So in this video, we're going to start mostly with just reviewing some stuff about hash maps, just because it's going to be on your project too. We want to make sure that we remember all the terms and highlight some points. I also want to show you some new applications and spend a little bit more time on some things I went through a little quickly in the last video on Friday. So for today's learning objectives for all our videos, we're going to be able to describe the properties of a good hash function and the role of a hash function in making a hash map efficient. And then kind of in the other videos, we're going to be talking more about invariants in trees. So evaluating invariants based on their strength and maintainability, and coming up with invariants for data structure implementations, comparing and contrasting the properties of runtimes of binary trees, binary search trees, and these things called AVL trees, and describing the AVL invariant, explaining how it affects AVL tree runtimes, and compare it with the binary search tree invariant. To be a little honest, we probably won't get too much into this idea of the AVL tree in this lecture. We'll probably focus that more on Wednesday's videos. So with that, let's talk a little bit about hashing. So as a reminder, we talked about this idea of hashing for hash maps being this really, really cool technique in computer science to make efficient lookups for something like a dictionary. And so we talked about kind of the state-of-the-art implementation is this thing called a separate chaining hash map. We have an array of fixed size where we treat each index in that array as a bucket. And we use a hash function that tells us for any key which bucket it belongs into. And we go to that bucket and we can create like a linked list or some type of list of values for all the values that collide there. And so this separate chaining hash map is what's used in Java behind the scenes in Java's hash map. It's a very, very important idea. And this is the thing you're going to be implementing for your next project, implementing this chaining hash map. And the reason we allow these chains, these buckets, is because when we're using hashing, we're going to have collisions. If I only have 10 spots in my array and I'm trying to put in 20 elements, there will be a collision there. And as a reminder, you know, the runtime for this chaining hash map is dependent on how long these chains get. And so we kind of talked a bit about the best case, which is where all of the keys are kind of really uniformly distributed over all the buckets. And then if they're all nicely distributed, then all the chains will be short. And then your runtimes for get, put, and remove will all be constant time if those chains are constant length. But in the worst case, everything's clumped together kind of in one bucket. Now these chains start getting longer, maybe order n length, and now your get, remove, and put calls will now take closer to worst case theta of n time. We did argue though that for separate chaining, in practice, it's actually really hard to get that worst case to happen. So it's much more common that you're going to be in this kind of in practice case, which is really close to the best case, which is basically constant time for all of your operations. And to give you a bit of intuition why this in practice case happens, it's because we're going to assume we're using a good hash function that distributes the values kind of around evenly. And we assume we're going to resize our hash table every once in a while, but not too often. And so when we say in practice, we mean it's almost always the case that it's going to be this theta of one runtime. But again, it's technically not a guarantee, right? Because cases don't just tell you about like, if this situation's happening, what's your runtime? Okay. So we said, as long as you don't resize often, how do you know when you should resize? As a reminder, we talked about how you want to resize when your load factor starts getting too large. As a reminder, the load factor is the number of elements in the hash map divided by the number of buckets available. So the size of the hash map divided by the length of its array. And if that ratio starts getting too large, then you're going to start expecting that some of those chains might be getting a little long, and now your runtime might slow down. And so usually what we'll do is we pick some threshold. Once lambda reaches some constant value, say 1, then you go and resize your table. And generally when you resize, you double the size of the array. And that's gonna, when we do this doubling trick, it's actually really infrequent that we're gonna have to resize many, many times. One of the things we talked about as a reminder when you're doing this resizing, implementing your code, I've said this quite frequently, but I wanna make sure you don't forget. Remember, when you resize, you don't just double the size of the array. You also have to rehash all the keys already in there to make sure that they go in the new correct spot. Now, one of the things we talked about towards the end of Friday's videos was this idea of how could we extend this notion of the hash table to work with any type of key? Because so far we just assumed that all the keys are integers, and then we just modded it by the table size to get the index. So in general, our definition of hash function is going to be more generic. It's going to be a function that can use any type of data as the input and map it to integer values that are going to be generally more constrained and easier to work with. Now, there are some properties we want of a hash function. We need it to be deterministic. What I mean by that is if you hash the string Santino twice, it should always result in the same value. If it were some like random number generator, well, that wouldn't be really good because then you wouldn't, when you put Santino in as a key in one call, and then if you called the hash function again, it generated a random number, then you wouldn't necessarily be able to get the right index. So these things need to be deterministic. We want them to be efficient. If we want our hash map to always be running in this theta of one time, we want our hash function to also be really fast. And our third property that we want is we want uniformity. What I mean by that is that the outputs of the hash function should be spread out evenly across the output range. So one valid hash function is every string gets hashed to the value 0. It's deterministic, it's efficient, it just returns 0. But I would argue that's not uniform because now everything would be sent to the same bucket. And so you want your hash function to take advantage of all of the information it has available to it, all the information in the string, and return a number that somehow represents that, so that similar strings or different strings don't get hashed to the same place. Collisions will still happen. That's good. You can represent more strings in Java than simple integers, but we want to reduce the number of collisions essentially. So for hashing, there's a lot of things you could do to come up with a hash function. So in this slide, I'm going to walk through some hash functions for the string type. One thing I'll mention is that you're not going to usually spend a lot of your time writing your own hash functions. Usually when we're programming with data structures, we are just going to use the hash functions that someone else wrote for us. So Java has these hash functions built in for various objects, and we just use those instead of having to come up with my own. There's a bit of an art and a science to coming up with a good hash function. And what we want you to be able to do is just understand the patterns, like why one might be better than another. We're not going to ask you to like memorize these or be able to write them from scratch, because no one's ever going to do that. So remember, hash function needs to take a string, in our context string, but again, any type, and turn it to an integer. So the simplest one you could think of is, well, let's just hash by the length. The length of the string is a number, so I could just grab its length and return that as the hash code, or the value of the hash function. Now this works. It's a hash function. It's better than just returning some number like 0. I would argue it's pretty fast, and it's deterministic, so it meets all three of our goals. Now, one downside of this hash function is it does lead to a lot of collisions. And sometimes it's not very clear when you look at a hash function, like how many collisions will this run into? One heuristic you can use is how easy is it for you as a person to look at this and figure out two strings that will collide? And in this case, if you return just the length of the string, any string of the same length will also have the same hash code. So if you have the string cat and dog, both of those have the same length, and so they'll collide. And since that's pretty easy for you to look at and figure out two strings that collide, you could assume that there could be a lot of collisions because, maybe some adversary that's using our data structure could just really easily come up with these strings to give you this kind of worst case collision runtime. So the reason this first implementation doesn't quite hit everything is it throws away a lot of information about the strings. It doesn't take into the characters at all. So one thing we could do is we could try to incorporate character information. So the idea here is that strings are made up of characters, and in programming languages, particularly in Java, each character is represented by a number. So for example, the letter A corresponds to the number 97, B is 98. There's this whole encoding scheme on your computer that tells you kind of when the computer sees a number, what characters that correspond to. So one thing we could do is we'll just treat each of those characters like a number and then add them all up. So take all the character values in the string, convert them into numbers, which we're doing with this casting operation, and then add it up to one big number. And this one also works great. It's also still really fast, and there's fewer collisions than the first one. But we talked a little bit about on Friday that it's still a little easy to come up with collisions. It's not as easy as the first one, but if you're just adding up the characters, then any change in the ordering is also thrown away. Those would also collide. So we showed in an example, God and dog are two strings that would hash to the same value here because they're composed of the same characters, just in a different order. So any anagrams would also be collisions here. So the last and best hash code that's used in pretty much every programming language for at least string types is one that's very similar in theory. It's looping over all the characters, adding them up, but it multiplies each character by usually some prime number. It's kind of the math is complex. Don't worry about the actual code or how to compute it. But what it's doing is it's very similar to implementation 2, but each character is multiplied by some number such that that number differs on each iteration of the loop. And because it's different on each iteration of the loop, now order matters. So God and dog will now hash to different things. And this one is going to have very few collisions. But a con here is it's a little bit slower because there's a lot of math going on. It's a lot harder to understand. And it turns out that most implementations of this hash code result in gigantic numbers for like the output. And some of them might even be negative. And so that's actually one thing you have to worry about in your implementation is these hash values might get really, really large or really, really small and how to work with those. So as a reminder, we don't care that you actually know how to implement this hash code from scratch, but do understand how these things relate to each other, why one is different, how they're different, what they're trying to solve. And this third one is the one that's used mostly in practice or something similar to it. And one of the reasons I can try to argue to you that there are fewer collisions here is I can't think of two strings that collide with this input. Now, there's a lot of details I'm hiding here, but it's really hard for people to just look at this and say, oh, these two strings collide, which means it's probably doing a really good job of spreading values out. Now, for the most part, as I mentioned, you are not going to be worrying about implementing your own hash code or your own hash functions. The way Java is designed, every object has a hash code method, and that hash code method does the magic of making a good hash for the object types that Java implemented. So strings and other types have a built-in hash function that's good. You should just assume it's good. So you should just use that whenever you can. Now, one thing to remember is that the hash code is going to give us an int representation of the object. It's going to say, oh, the string Santino is like the number 504. But we, as the implementers of the hash table, we still need to constrain those gigantic integers to our table size. So there's usually a two-step process here, where you call the object's hash code to get the int representation, and then we mod it by the number of buckets to get the right index, to get the right bucket size. So that's usually that two-step process. Now, one thing that we didn't talk about on Friday are some interesting applications of hashing that aren't very clear when you just think about hashing. You're like, okay, I could see how we use hashing for hash maps, but where else is this used? This is used all over the place. So whenever you're thinking about caching files, you most of the time don't think about caching files, but usually if I go to a website, say like Facebook, every time I go there, they try their best to make the page load time fast. Is if they don't have to resend me a bunch of files that they already sent me before, like the files for like my profile picture or things like that. What your browser tries to do is it tries to cache results. And so it will save some resources, some artifacts that it downloaded the first time, and it will just use those in place instead of going all the way to Facebook servers and back again. So if you've downloaded these files, one thing you need to make sure, one of the really hard parts about caching, saving things temporarily, is knowing if they ever get out of date. So like, do I need to actually go to Facebook and get the new resource because maybe it's been updated? And the way we implement this is along with every resource, we send a hash of it. So you send both the file contents and you take all the data in the file or whatever you're trying to send, and you turn it into a hash value. And you send that hash along. And then when people are wondering, oh, is this out of date? They just have to check the hash. Because if my file is the same version as your file, well then our hashes will be the same. And so we could just exchange those hash codes to verify very efficiently if I'm up to date. Now, if our hash codes differ, then I know that your file is different than my file, and now I need to go ask you for the new version of the file. Now, there's a small chance that two files that different will hash to the same value, and then you will falsely think you're up to date. But that doesn't happen very often. These hash functions are designed to be really, really good at avoiding collisions. This very similar process is used to make sure that your computer is secure. So usually when you download a file, it comes with a hash of the file contents. And before your computer will open the downloaded file or anything like that, it makes sure that the file that it actually downloaded matches with that hash it was sent. And the reason there is maybe some nefarious actor intercepted your communications while you're downloading the file and maybe replaced, I don't know, some app you were downloading with a virus. And it would be really hard for them to inject a virus in there and also change the hash code to be kind of something that's consistent with their new code. So very, very tricky, but very clever application of this. And you're actually all very familiar with one application of hashing now, which is, again, similar in notion to all of these, but this idea of fingerprinting. So you've all been using Git. Every time you make a commit, it makes a hash of all of the files that you've changed in the state of your repo so far. And that hash is what it uses to label the commit. So you've probably seen these kind of weird strings in your GitLab of like the commit ID. This is a hash that is used to identify these things. In lots of other places, we use hashing to identify content. So to give you an example of one of the things that people do in industry, when you're thinking about using applications of hashing to fingerprint something or to verify something, you always need to figure out what the salient features are of your data. So for example, if you're working with strings, does it matter if the strings are uppercase or lowercase? If it doesn't matter, then your hash function can take that into account, maybe lowercase all strings before trying to hash them. Similarly, if you want to try to figure out hashing some other type of data like images, trying to figure out what's important to hash and what's not, what should your hash function include and what's not, is a really interesting design decision that people take on to make sure that their applications work. So just for example, if you wanted to use this caching thing, you want to use a hash function, turn this into a number, send that along. Well, does it matter if the image has been flipped? It might matter, it might not, depending on your application. And so you might, think as a developer, trying to think about how can I write a hash function that's the same no matter if the image is flipped or not. So there's lots of things that you kind of go into determining what's salient and what's not. Now, as a quick reminder, some other things we introduced in the video that's going to be helpful is this idea of the iterator. So being able to iterate over your objects. For our hash table, we need to iterate over the buckets. And so the iterator is an interface that we're going to provide a class for that kind of shows how to iterate through these values. And so there's multiple ways of using this iterator, but you can review this stuff from the slide from what we talked about in 143. And as a reminder, do start this project 2 iterator thing as early as you can, because this is generally the thing that's probably the most tricky for students. That's all I have about hashing for today. In the remaining videos, I want to talk about trees.